Ever wonder how your phone, like, displays that perfect picture you just took? Or, like, how it plays your favorite music? It's all thanks to something surprisingly simple. On and off switches.
Okay.
Welcome to the deep dive. Today, we're going to unlock the fundamental language of your computers. Binary numbers.
Oh, yeah.
You, our amazing listener, shared some really insightful video recordings from a computer science teacher.
Yeah.
And we're going to use those as our launch pad to really understand what binary is, how it underpins basically all digital technology, and even explore some of its fascinating capabilities and then some limitations too.
Absolutely. This might seem like a pretty, foundational topic.
Yeah.
But honestly, even with a basic grasp of this, I think you'll start to see the digital world around you in a whole new light.
Sure.
Our mission here is to go beyond just, defining terms.
Totally.
And really get to those, aha moments about how your digital life is built on this simple foundation of just ones and zeros.
Okay, so let's dive straight into it. What is binary at its core?
So fundamentally, binary is a number system, like our decimal system, right? But instead of using 10 digits, it only uses 2, 0 and 1.
Okay.
You can think of it like this. It represents the most basic electrical states inside of a computer. So 1 signifies that an electrical signal is present, it's on.
Okay.
And 0 means that it's absent, it's off.
So it's like the fundamental building block,
Yeah.
on or off.
Precisely. And each of these individual zeros or ones, we call that a bit.
Okay.
Short for binary digit. Now these bits, they rarely work alone, right? Computers group them, commonly into sets of 8. And this group of 8 bits, we know this as a byte.
A byte.
The basic unit for measuring all digital information,
Right.
whether it's the size of a document or the capacity of your phone storage, it all comes down to bytes.
That makes sense.
And here's a kind of neat little connection I think you'll like.
Yeah.
That power on-off symbol that you see everywhere, right? Like the circle with a line through it.
Yeah.
That's actually a stylized representation of a 1 and a 0
Oh,
on and off. It's kind of cool.
I never thought of it like that. That's a cool visual. Okay, so we have these on-off switches, these bits forming bytes. How does this translate into my computer actually, doing things?
It's fascinating, really,
Yeah.
how this incredibly simple, duality can power all the complexity that we see on our screens every day.
Right.
Inside your computer's CPU, the central processing unit, there are literally billions of tiny electrical switches.
Oh, wow.
Called transistors. And these transistors, they're controlled by those on-off signals,
Okay.
the binary code, and different combinations of those on-off states will represent different instructions and data, of course.
So the apps that I'm using, the music that I'm streaming, even these recordings that we're doing right now, it's all ultimately translating to vast sequences of ones and zeros, right?
Exactly.
That tell those transistors what to do.
You got it. It's all converted into these binary instructions that the processor can then execute. And, what's important to note, I think, is that the same binary sequence can represent a whole bunch of different things depending on the context.
Really?
So for instance, the binary sequence, let's say 01000000.
All right.
That could represent the uppercase letter A.
Right.
When your word processor is encoding text, right?
Right.
But if that same sequence is being used, let's say in a game,
Yeah.
it might be the instruction that tells your character to move to the right.
Oh, interesting.
So it really depends on the surrounding software and hardware, how they're interpreting that binary based on what's happening at that moment.
So it's like the computer has all these different rule books.
Right.
It's applying to the same set of symbols.
Yeah.
That's fascinating. Now, you're talking about billions of bits. It sounds incredibly complicated.
Yeah.
How do we even begin to manage that?
Well, that's where the beauty of abstraction comes in. So think of abstraction as a way of basically hiding all that underlying complexity.
So we can work with things at a higher, more intuitive level. Because yes, at the lowest level, everything is represented by these bits, these on and off signals.
Yeah.
But thankfully, as users, we don't need to worry about the intricacies of binary. We can still use our devices pretty effectively, right?
Thank goodness.
It's similar to, let's say, driving a car. You interact with the steering wheel, the pedals, the dashboard. You don't need to know how the combustion engine works.
Or the intricacies of the transmission, right?
Right, to get from point A to point B.
Exactly.
So you're saying the computer kind of handles all those low-level binary operations in the background, allowing us to interact with more user-friendly interfaces.
Precisely. So let's say you're sending a text message, just a simple one that says, hello.
Okay.
You type the letters on your keyboard, right?
Right.
Behind the scenes, what's happening is your phone is using a character encoding system, like ASCII or maybe Unicode. And what these do is they assign a unique decimal number to each character. So like H has one number, E another, and so on.
Okay.
Then your phone will take these decimal numbers and convert them into, you guessed it, binary, those sequences of ones and zeros, and then that gets transmitted over the cellular network. The recipient's phone then decodes that back through that same process to then display those letters that you typed. So hello appears on their screen.
It's like layers upon layers of translation that's all happening invisibly. That's amazing. What about images and videos?
Yeah.
They're so visually rich. How does that work?
So images are composed of tiny picture elements called pixels.
Pixels.
And each pixel has a very specific color. And that color is typically represented by what we call the intensity of red, green, and blue light. It's like those three primary colors of light.
Okay.
And each of these color channels, red, green, blue, is assigned a numerical value. It often ranges from 0 to 255. And this dictates how bright that specific color component is for that pixel. And as you might have guessed by now, these numerical values, they also get converted into, guess what?
Binary.
Binary, to be stored and then eventually displayed.
Wow.
And videos are essentially just a very rapid sequence of these still images, along with audio data, of course.
Right.
All encoded in binary.
It all comes back to those ones and zeros. That's crazy. Now, the videos you mentioned, they also touch on the distinction between analog and digital data.
Right.
What's the key difference there that we should understand?
So analog data is information that's represented by like continuous physical quantities.
Okay.
You can think about like a traditional painting where the colors blend seamlessly, or a vinyl record where the sound is encoded as like continuous grooves in the vinyl.
Oh, okay.
But digital data, this represents information using discrete values.
Okay.
Those distinct ones and zeros we've been talking about.
So like my old photo albums, the ones with the physical prints.
Yeah.
That's analog.
Analog.
But the photos I take on my phone and store on the cloud, that's all digital.
Exactly. And you know, more and more these days, we need to bridge the gap between these two forms of data.
Yeah, for sure.
Like think about digitizing old family photos to preserve them.
Right.
Or converting analog music recordings, like from your vinyl, into digital files so you can share them more easily.
Yeah.
Or play them back on different devices.
Totally.
Now, this conversion process, it inherently involves abstraction.
Yep.
When you scan a photograph, for example, you're essentially capturing its visual information as a grid of discrete pixels with specific color values that we talked about earlier. And while a good scan can capture a lot of detail from the original, you might inevitably lose some of the like subtle nuances and textures that were present in the original print.
So there's always a chance or a potential for some information to be lost or maybe altered during that analog to digital transition.
That's definitely a key consideration. So to represent like the continuous nature of those analog signals in a digital format, we use a technique called sampling.
Sampling. Okay.
And so for audio, this means that we measure the amplitude or the loudness of the sound wave at very regular intervals.
Good.
These measurements are then converted into binary numbers, and that forms our digital audio file. You can almost think of it like taking snapshots of a moving object. The more snapshots you take per second, the higher the sampling rate, the more accurately you're going to capture that movement.
Okay, yeah.
Similarly, like a higher sampling rate in audio, that's going to capture more of the nuances from the original sound. The trade-off, though, is you end up with a larger file size.
Right, that makes sense. More accuracy often means more data.
Yeah.
Now, using these bits and bytes to represent everything sounds really efficient. But are there any inherent limitations to this digital approach?
That's a very important question. Because computers rely on this fixed number of bits to represent the data, this inherently imposes limitations on the range and precision of the values that they can actually handle. Imagine, like, you're trying to measure the length of a room, but you only have a ruler with markings for whole inches.
Yeah.
You can't get a perfectly precise measurement if the actual length of the room falls somewhere between those 2 inch marks.
Right, you're limited by the resolution of your measuring tool.
Exactly. And so this is kind of how it is in the world of computers too.
Interesting. How does this play out, practically?
So for whole numbers, which we call integers, programming languages will allocate a specific number of bits.
Okay.
Like 8 bits, 16 bits, 32, 64. You've probably heard of those.
Yeah.
That number of bits determines the range of integer values the computer can represent.
Okay.
So for example, a 32-bit integer can store a huge number of values, roughly 4 billion different values. But what happens if a calculation results in a number that's larger than that maximum?
Right.
You get what's called an overflow error.
An overflow error.
And this isn't just like a theoretical problem. A famous example of this is the Ariane 5 rocket.
Really?
Yeah, it crashed because of an integer overflow in its navigation system.
Oh, no.
Yeah. The 16-bit integer that they were using, it wasn't large enough to hold the value that it needed, and it led to a critical system failure. And that seemingly small detail about the number of bits being used, it had huge real-world consequences.
Wow, a rocket crashing because of a limitation in the number of bits used to store a value.
Yeah.
That really highlights the practical implications here.
Yeah.
What about numbers with decimal points, like pi?
Yeah.
Which goes on infinitely, right?
Exactly. So real numbers like pi that have these infinite decimal expansions, they can't be perfectly represented if you're only using a finite number of bits.
Right.
And this leads to something called rounding errors.
Rounding errors.
So because the computer can only store a limited number of digits, it has to approximate the number by rounding it to the nearest representable value that it can handle. Think about it, like in financial calculations.
Yeah?
Even tiny rounding errors, if they accumulate over millions of transactions,
Yeah?
can lead to significant discrepancies. That's why banking systems have very specific ways of handling those small fractions.
Wow. So it's like trying to fit an infinitely detailed picture into a frame with a limited resolution.
Yes.
You lose some of the fine detail.
You got it. And different computer systems and software, they might use varying levels of precision when they're representing these numbers.
Yeah.
Which means their approximations of the same number, like pi, might differ just slightly. And while these differences might seem super minuscule, insignificant almost,
Right.
they can compound over a series of complex calculations. And that can lead to noticeable variations in the final results. Imagine two different programs, they're both calculating the trajectory of a satellite, but they're using slightly different levels of precision for their value of pi. Those tiny rounding errors over those long distances could lead to pretty significant deviations in where that satellite ends up.
Wow.
So the rule of thumb is, the more bits you use to represent a number, the greater the precision and the smaller the potential for those rounding errors to creep in.
Makes sense.
Now, modern systems, 64-bit systems, they offer a fast range, for integers and these floating point numbers. But that fundamental limitation of having a finite representation for an infinite value, that's always going to be there.
Okay, I'm starting to wrap my head around this. We've explored what binary is and some of its interesting consequences, I guess.
Yeah.
Now let's dig into how it actually works.
Okay.
How do we translate between that binary language of the computer, the ones and zeros, and the decimal numbers that we humans use every single day?
Understanding this conversion process really helps, I think, to solidify the whole concept. So all number systems, including decimal, which is base 10, and binary, which is base 2, they operate on the same fundamental principles of place value.
Okay.
Let's quickly revisit decimal, right? You take the number 5, 0, 12.
Okay.
The 2, it's in the ones place, right? That's 10 to the power of 0.
Right.
The 1 is in the tens place, it's 10 to the power of 1.
Oh.
The 0 is in the hundreds place, 10 to the power of 2. And then the 5 is in the thousands place, that's 10 to the power of 3.
Right, the familiar powers of 10. So with binary, is it the same concept, but with powers of 2?
Exactly, you got it.
Okay.
In binary, each position represents a power of 2, and they increase from right to left. So let's take the binary number 1101, the rightmost one, that's in the 2 to the power of 0 place, which is just 1. Moving left, you have a 0, that's in the 2 to the power of 1 place, which is 2. The next one is in the 2 to the power of 2 place, which is 4. And then the leftmost one is in the 2 to the power of 3 place, which is 8.
Okay.
To convert that binary number to decimal, you simply add up the place values where a 1 appears.
Okay.
So you've got 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1. That all adds up to 13.
13.
So binary 1101 is equivalent to the decimal number 13.
Okay, got it. So each position in binary is like a doubling value as you move to the left.
Yeah.
How do we go from our familiar decimal numbers into binary?
So to convert a decimal number into binary, you basically figure out which powers of 2 can add up to that decimal number.
Okay.
So let's take the decimal number 41.
Okay, 41.
And let's consider the powers of 2. 1, 2, 4, 8, 16, 32, 64, and so on. The largest power of 2 that is less than or equal to 41 is 32. So we'd put a 1 in the 32's place in our binary representation.
Okay.
We subtract 32 from 41, that leaves us with 9. The largest power of 2 that's less than or equal to 9 is 8, so we'd put a 1 in the 8's place. Subtracting 8 from 9 leaves us with 1, which is 2 to the power of 0. So we place a 1 in the 1's place. For all the other powers of 2 that we didn't use, the 64, the 16, the 4, and the 2, we put a 0. And reading from left to right, the binary representation of 41 would be 00100001.
That's, I think I'm starting to see it.
Yeah.
It's like repeatedly finding the largest power of 2 that fits, and then you kind of keep going from there.
Exactly.
Let's try a practice one.
Yeah, let's do it.
What is the decimal equivalent of the binary number 01000101?
All right, so let's apply the place values. Starting from the right, we have a 1 in the 1's place, a 1 in the 2's place, a 1 in the 4's place, a 0 in the 8's place, a 0 in the 16's place, a 0 in the 32's place, and then finally a 1 in the 64's place.
Okay.
Summing all of those up, 64 plus 0 plus 0 plus 0 plus 4 plus 2 plus 1 equals 71. So the binary 017901111 is 71 in decimal.
Okay.
Yeah.
Nailed it. Here's another one. What about 011111 in binary? What's that in decimal?
Okay, so same method. 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 all sums to 127. And actually notice a little pattern here. When you have all ones from the right up to a certain place value, the decimal equivalent is always going to be 1 less than the next power of 2. So in this case, we have 7 ones.
Right.
2 to the power of 7 is 128. So 127 is 1 less than that.
That's a handy shortcut to keep in mind. Yeah. The videos also gave this practical scenario about sequential ID numbers in binary.
Right.
So let's say the last assigned ID was 101,011. What would the next ID in that sequence be?
So one straightforward way to solve this is to first convert that binary ID, the 1 on 1011, to its decimal equivalent. So we've got 128 plus 132 plus 016 plus 1 half plus 1 1, which gives us 163. The next ID in the sequence would simply be 1 and 63 plus 1, which is a 164. And now we need to convert that 164 back into binary. So the largest power of 2 that is less than 164 is 128. So we have a 1 in the 128's place. Subtracting 128 from 164 leaves us with 36. The largest power of 2 less than 36 is 32, so we'd have a 1 in the 32's place. 36 minus 32 leaves us with 4. So we would need a 0 for the 16's place and the 8's place, and then we'd have a 1 for the 4's place, and then a 0 for the 2's and 1's place. So the next binary ID would be 100 and 100.
It's interesting to see how we can convert, increment, and then convert back.
Yeah.
It all works together. Finally, the videos talked about the power that even a small number of bits can provide. Can you elaborate on that a bit more?
Absolutely. This is where the efficiency of binary really shines through. When you add just one single bit to the number of bits that you're using, it doubles the number of distinct values that you can encode.
Oh, wow.
It's really powerful. So consider 3 bits. With 3 bits, you can have 2 to the power of 3, which is 8 possible combinations. So from 000011, you can represent 8 different values, typically 0 through 7.
Okay.
Now, if you add just one more bit, giving you 4 bits, you can have 2 to the power of 4, which is 16 possible combinations from 0000 to 1111. And that doubles your range from 0 through 15.
It's like exponential growth.
Exactly. It's incredibly powerful.
So if 1 byte, which we know is 8 bits, allows us to represent 2 to the power of 8, or 256 different values, how many bits would we need to represent exactly 512 distinct values?
Since 512 is double 206, you would need just 1 additional bit. So 9 bits, or 2 to the power of 9, can represent 512 unique values. This doubling effect with each added bit is fundamental to how computers can store and process massive amounts of information.
Wow. This has been a really enlightening deep dive, I think, into binary.
Yeah.
So to summarize, from these videos, we've seen how computers use this simple concept of on-off switches, represented by zeros and ones in binary as their core language. And then these bits are organized into bytes. And we have this principle of abstraction, thankfully, that shields us from all that low-level complexity.
Right.
We've explored how analog data from the real world is converted into a digital format through sampling. And we've learned about, some of the inherent limitations of using a fixed number of bits, which can lead to those overflow errors and the rounding errors that we talked about. And finally, we kind of dug into the actual mechanics of converting between binary and decimal numbers.
Yeah.
And I think we've all come to appreciate how adding even a single bit can significantly expand that representable range of values.
Exactly. And I think understanding these fundamental concepts really provides you, the listener, with a much richer understanding of, like, the inner workings of the digital world that you interact with every single day.
Absolutely.
From the most basic functions on your smartphone to the most intricate algorithms that are running on, powerful servers somewhere.
Now that you've grasped how the entirety of the digital realm boils down to, like, at its core, sequences of ones and zeros, I'm going to leave you with this.
Yeah.
What other seemingly intricate systems in our world might be governed by surprisingly simple underlying principles? It's just a fascinating thought to carry forward.
Yeah,
Thanks for joining us on this deep dive.
Thanks for listening.